So, and it can get kind of complex, so I'm going to do my best to try and make this as smooth as possible, but I can't guarantee anything. I really want to challenge myself by trying to convey some of this information. So, regarding special relativity, which is what I want to talk about, does anyone have just a general definition of what special relativity is?
I don't really know, but relativity has to do with relative stuff. And all I know about that is, like, if I was driving 50 miles per hour next to another car driving 50 miles per hour, our relative speed to each other is 0. Or if I was driving 50 miles per hour in one direction, the other car was driving 50 miles per hour in the other direction, our relative speed between ourselves would be 100. That has to do with kind of like something about, like, I don't know, the way that I see something else happening, and what they would see about what's happening with me or something like that.
So in the case of special relativity, it has to do with comparing physical quantities between inertial reference frames. So, like Mr. McDonald said, from one frame of reference, the velocity of an object could appear different from another frame of reference. If I'm on a boat moving 5 meters per second and I throw a ball at 10 meters per second, it looks like it's moving 10 meters per second. But to a stationary observer on land, it looks like it's moving 15 meters per second. Right? It's all up to that reference frame. And so, regarding special relativity, Einstein had 2 postulates that he based the theory around. The first one is that the laws of physics are constant in all inertial reference frames. And that word inertial just means that these reference frames are undergoing no acceleration. So they can be moving with a certain velocity. It's just that that velocity is constant. And then the second postulate is that the speed of light in a vacuum is the same for all observers, no matter what. No matter what your reference frame is, it always appears constant.
Wait, so I have a question. So even if your reference frame was moving, it would appear the same as to someone whose reference frame wasn't moving?
According to mathematics, that's how it works. Now, of course, I can't say for sure because I've never experienced
You've
that.
never been in a vacuum watching the speed of light?
No, I haven't. But apparently, it's supposed to be the same no matter what, which doesn't seem to make sense when you hear it, but I guess we just gotta accept that. So, to start, I'm going to suppose that I have 2 mirrors. I have a mirror here and a mirror here. So imagine you're riding a moving rocket, and you, while on the rocket, watch a photon, let's say this is our photon, bounce between these 2 mirrors. So the photon is going to go up, and it's going to come back down, and it's going to keep doing that. It's going to keep bouncing between the mirrors on this moving rocket, and you are on that rocket, okay? The photon's path, the distance it travels, is of length ct. T is time, c denotes the speed of light, and distance is, speed times time, right? So this is going to be of length ct. And then this can be O for the observer on the rocket ship watching. Now to someone outside of this ship, let's say on Earth, if you were to somehow watch this beam of light, you would have a moment in time here, and you would have a moment in time here. But to the observer that is out here, this beam of light doesn't appear to be a straight vertical line of ct this length. It appears to be diagonal like this, and we're going to call this ct prime. Now, if you notice, the y component of this line right here is of equal length to CT. And it's obvious that CT prime is greater than CT. So what that implies is, if the speed of light, c, is the same for all inertial reference frames, that means that the value of t somehow must be different for these two observers. Yes?
What does inertial reference frame mean?
So the inertial reference frame means that it's just not undergoing any acceleration. So it could be moving with a velocity, but it's not accelerating. Now, this line down here, let me draw just the basic CT prime, and then we're going to call that the CT. This line down here, this x component of the triangle, is going to be equal to VT prime, according to this observer, because as the rocket travels, it's traveling with a certain velocity, and then again, velocity times time is that distance. So we have the speed of light times some sort of change in time, CT prime, and then we have CT over here, which is the time according to observer O over here, and then we have VT prime, which is the velocity of the ship that this observer out here sees, and the time that this observer out here experiences. Now, of course, this creates a right triangle. So if we recall some pretty fundamental geometry, I hope you can all recall it. There's something called the Pythagorean theorem. You guys are familiar with it, right? Yeah. Okay, good. So what that means is CT prime squared equals CT squared plus VT prime squared. Now, if you solve for CT, that means, and we're going to denote this as C squared T squared instead of CT squared in parentheses. C squared T squared equals C squared T prime squared minus V squared T prime squared. Now there's a common T prime squared, so that means C squared T squared equals T prime squared C squared minus V squared. If we divide both sides by C squared and T prime squared, we're going to get rid of this C squared here. So that's simply going to become T squared over T prime squared equals, and then this T prime squared is going to go away, and then that's going to become C squared over C squared minus V squared over C squared. Therefore, if you take the square root of both sides, you're going to get T over T prime equals the square root of 1 minus, because C squared over C squared is 1, right? 1 minus V squared over C squared. Now what this means is T prime, the time that the observer outside of this rocket ship experiences, is equal to T over the square root of 1 minus V squared over C squared. Now with that being said, if T prime, and I'm going to introduce something probably new to you, well, the letter itself may not be new, but it's going to be a lowercase gamma. Now, t prime also equals gamma t. So if t prime equals t over the square root of 1 minus v squared over c squared, and it also equals gamma t, then that means that gamma must equal 1 over the square root of 1 minus v squared over c squared. And that gamma has a name. It's called the Lorentz factor. And the Lorentz factor can be used in order to change your classical physical quantities into quantities in relativistic physics. So, for example, momentum, mass times velocity. You would do gamma mass times velocity, which would turn into mass times velocity over the square root 1 minus v squared over c squared. That'll give you your relativistic momentum between inertial reference frames. Now, with this concept of the Lorentz factor, which is a very, very important concept in relativity, in any of the math you do in relativity, you're going to need that Lorentz factor. And I'm going to rewrite the Lorentz factor over here. Again, Lorentz factor gamma equals 1 over the square root of 1 minus v squared over c squared. And so the first consequence of special relativity that I want to discuss is time dilation, which was implied by the example that I gave with the mirrors. If the value of c, the speed of light, is constant no matter what, that means there had to have been a change in time in order for the distance the light traveled in order for it to be greater. And I said that t prime equals t over the square root of 1 minus v squared over c squared. T prime is the time for the observer outside the ship, and t is the time for the observer on the ship. So if we go back to the example with the observer on the ship bouncing a photon between mirrors, let's just assume that for this observer on the ship, 1 hour passes. So time t is equal to 1 hour, which is 3,600 seconds. So we know that this dilated time is equal to 3,600 seconds over the square root of 1 minus v squared over c squared. Now let's also assume that that ship is traveling at 80% the speed of light. And the speed of light, again, is denoted by c, and 80% the speed of light is equal to 0.8 c, which means t prime would equal 3,600 over the square root of 1 minus, and we said the velocity was 0.8 c. So 0.8 c squared turns into 0.64 c squared. Over c squared. Now, of course, I can reduce this by getting rid of the c squareds. So t prime equals 3,600 over the square root of 1 minus 0.64. 1 minus 0.64 is 0.36. So this equals 3600 over root 0.36. Root 0.36 is equal to 0.6. So then this turns into 3600 over 0.6. 3600 divided by 0.6, I had to look at my notes for that one, equals 6,000. So essentially what all this means is the time for an outside observer, T prime, equals 6,000 seconds. For every 3,600 seconds, the observer inside the rocket ship experiences. Which means for the observer in the rocket ship, time must be moving by more slowly. And so, again, speed of light is constant. And so in order for that diagonal line to be made between the mirrors, which is between moments in time, the time passing had to have been greater in order to create a greater distance, CT prime, than the initial distance, CT. Is this confusing at all? It might, if it is, it probably is. Again, I'm not an expert at this, so if it is confusing, I totally understand.
I think I sort of get it.
The actual math itself is just substituting in values. So that part isn't difficult. It can just kind of be the notion of time somehow changing between reference frames, right? And now another concept that I would like to cover.
Can I ask a question?
Yes.
What's up with the twin paradox?
The twin paradox. I've heard of it, but I'm going to be honest with you. I don't really know what the twin paradox is about.
Anybody know anything about the twin paradox? Has anybody seen Interstellar?
You showed it to us in class last.
You've seen it? Why? What's weird? What was weird about it? Right? It's a good movie. It's kind of weird, right?
Very.
What got weird? Did you see it?
I've seen it myself.
It's like that dude went back in time, or like he was like parallel to himself in a different time scene.
Right, or something.
Seemed like something about his age and his daughter's age, and
How they
at some
could
point,
reach the same age.
Hmm? At some point they were the same age, and then at some point his daughter's older than he is, right? Weird stuff with that. Yes? I mean,
Yeah.
that would seem odd, I think. Does that play into it at all?
Well, eventually, if you spend a long enough time in the ship, then an observer on Earth should be able to exceed your age, you think.
Because, well, because if when you're in the ship, wouldn't you probably be moving slower than someone on Earth? Like, because a person on Earth is rotating around the Earth, which is orbiting this. I guess it depends on how your ship is moving.
Yeah, well,
So I think maybe an interesting thing here is how fast is any object on Earth moving at any one point in time? Like how fast is the Earth moving through space? What percentage of, because what I think what we see here is like, it's not about like moving fast, just moving fast. It's like how much of a percentage of C are you getting? Like how fast are we moving as a fraction of C? I think we could work out a calculation. I think you would find that we are moving at a very, very, very tiny percentage. Like, I don't know the actual number off the top of my head. I'm gonna guess it's more like 0.00001 C. And so,
Which is about 1, so it's you'd be moving about the same time.
0.000001 is not about 1.
Well,
It's about 0.
if you plug it into the equation of C, you said like 0.0001 of C.
Of C, but in that equation, the V is what we're referring to. The V is the speed of the ship.
Yeah.
And so if we replace V with 0.000001 C, what you'll get is 0.
Yeah, that would.
Which basically means that for regularly moving objects, or objects moving closer to like human earthly speeds, we don't experience this time dilation effect.
Yeah, the closer your velocity is to, well, if your velocity is 0, you'd see that it would just be 3,600 over 1.
Yeah.
Which is the same time, right? So the faster you're moving, the greater the time dilation effect would be. Slower you're moving, the less the dilation effect would be. Which therefore means that as I'm walking around with here, technically time is supposed to be moving slower for me. Which,
Well, like a very small amount.
yeah,
Mhm.
I mean, it's like negligible, but according to relativity, that's what's happening every single time I take a step and you guys are sitting down.
That's so weird.
Wouldn't it? I feel like there kind of becomes a problem with how we measure time, though, right? Because the way we measure time is sort of subjective to Earth's motion already.
Mhm.
And so it's like,
It gets tricky.
yeah.
And to continue off of this idea of time, I also want to talk about another quantity that we can calculate through special relativity, and that's relativistic velocity. And you can find relative velocities between reference frames via something called a Lorentz velocity transform. Now, the mathematics behind this can get kind of hard to follow. And I'm gonna do my best to not mess up if I'm gonna be candid.
Before you get into the transformation, is there any practical use for understanding anything about relativity? Because it seems like this is some wacky stuff about children being older than their grandparents and like stretching, and it just seems weird.
Maybe at some point if we had the capability to travel at extremely high speeds, or if you're traveling near immense gravity, that would be more like general relativity, but something like that, potentially.
Yeah, potentially. I think even something closer to home. And what you were kind of pointing to is, I think what you were kind of getting at is like a satellite.
Yes.
A satellite to Earth is moving at significant speeds, not quite very close to, but some percentage of c. And our entire global positioning system and time accountability system functions by communicating with these satellites, right? And so there are these relativistic accommodations that are made for this idea, which is actually a real thing based on a lot of experiments, that time shrinks and stretches. And with the satellites it does so, and we have to correct our phones a little bit every instant throughout the day, and without making those little corrections, our time would be wrong. So everybody on the earth at all times are utilizing this very weird idea.
And also, too, one motivation for Einstein's relativity was Newton's laws didn't fit the path of Mercury. I think it was Mercury's orbit around the sun. And relativity, in a way, kind of accommodated for Mercury's unusual orbit. So let's say I have an XYZ plane, and this is gonna be frame F. And then we have a point on this x-axis here, x. And then I also have an x prime, y prime, z prime plane. And this is gonna be frame F prime. This is gonna be a point, or excuse me, that's a z prime, that should be an x prime. And I have a point x prime on the x prime axis. And I have a particle P moving with a velocity u prime x. And this entire reference frame here that encompasses this particle P that moves at a velocity of u prime x is moving with a velocity of v. Now, what I want to do is I want to express this velocity u prime of x that is with respect to f prime, which is moving with a velocity of v with respect to f. So I want u prime of x with respect to f. And in doing that, I can do a Lorentz velocity transformation in order to try and find that value. And something to note is that a point along the x-axis is found through x equals the Lorentz factor times x prime plus vt prime. And the time at which an event at x prime occurs, we can find the time it occurs in the frame of f as t equals the Lorentz factor of t prime plus vx prime over c squared. And these values come from an entirely different transformation called the Galilean transformation. To be frank, I don't want to do a transformation within a transformation, or a derivation of a transformation within a derivation of a transformation. So I'm just going to leave that there, and I'm not going to go over why that is. Now, an expression for ux, which is the velocity of the particle, which would be in frame f, well, we know that velocity is the derivative of position with respect to time, right? So we can say ux equals dx over dt. However, we have to utilize the chain rule because x is a function of t prime, which in and of itself is a function of t. So ux equals dx over dt prime times dt prime over dt. And this can be simplified into, well, not simplified, but I'm going to change the form of it. Dx over dt prime over dt over dt prime. And up here, I have x equals Lorentz factor times x prime plus vt prime, and t equals Lorentz factor times t prime plus vx prime over c squared. So this can become ux equals Lorentz factor derivative with respect or of x prime plus vt prime, and then that'll be over dt prime, and then all of that will be over gamma derivative t prime plus vx prime over c squared dt prime. Now these Lorentz factors here, we can get rid of them. then what's gonna happen, let's start with the numerator. So we have a dx prime plus dt prime over dt prime. That's gonna become dx prime over dt prime plus d, and we have vt prime over dt prime. And this is going to simply become dx prime dt prime plus v. And then the bottom down here, we have dt prime plus vx prime over c squared over dt prime. And then this is going to become dt prime over dt prime plus v over c squared times dx prime over dt prime. Now this dt prime over dt prime is going to just become 1 plus v over c squared times the dx prime dt prime. Now we said that dx over dt is equal to ux, which is what we're looking for. So dx prime dt prime is equal to this u prime x. So essentially what we get is ux equals u prime x plus v, u prime x plus v over 1 plus, and then we get v over c squared times u prime x. And this can also just be, this is how I typically write it, that would just be v u prime x over c squared. So if I'm given the velocity of this reference frame and the velocity u prime x with respect to this reference frame, I therefore should be able to find the velocity of u prime x with respect to reference frame f. I actually have an example here. And so that derivation looks very interesting. But again, all it is, when it comes down to it, when you're given an example problem, is it's just substituting values in for u prime x and v. So let me get some new reference frames here. We got z, y, x. This is going to be reference frame f. And that's Earth. Alright. Now let me get my z prime, y prime, x prime, f prime. And we're going to have a rocket in this frame of reference. Oh yeah, I like that rocket. Do you guys like the rocket?
I love it.
So great.
Thank you.
Yeah.
And this rocket is moving with a velocity of 70% speed of light, 0.7 c, and it's going to launch a missile. And this missile that it launches is going to be moving at 0.8 c, 80% speed of light. So u prime x is the velocity with respect to an already moving inertial reference frame. So this entire reference frame is the rocket ship. This reference frame is moving at 70% the speed of light. And with respect to this reference frame that is moving at 70% the speed of light, this missile appears to be moving at 80% the speed of light. So what I'm trying to do is I'm trying to find how fast this missile appears to be moving in this stationary reference frame. And all I have to do is substitute my values in this equation right here. So if I have ux equals u prime x plus v over 1 plus v times u prime x over c squared, I get 0.8 c for u prime x plus 0.7 c for v over 1 plus, and then that would become v times u prime x is 0.8 c times 0.7 c over c squared. This becomes 1.5 c over 1 plus 0.8 c times 0.7 c is 0.56 c squared. So that becomes 0.56 c squared over c squared. Those can cancel out. So now we're left with 1.5 c over 1.56. If I were to take a peek at my notes, that would be 0.96 c. So what all that means is, for a reference frame moving at 70% speed of light, and the velocity of an object with respect to that already moving reference frame is 0.8 c, 80% speed of light, then that means according to a still reference frame, this object should be moving at 0.96 c. And it makes sense, because these two objects are moving in a common direction. So if this object is stationary, then this object should appear to be moving faster than it appears to be moving relative to this rocket ship, right?
Yes.
And there is a lot more that could be done. However, I think that is enough of a challenge for me to try and talk about in front of people.
Beautiful. I just looked up